All right, so we're going to continue on with the carboxylic acid chapter. We kind of talked about all the derivatives yesterday, but we said that really they're all similar in that they have some sort of electron withdrawing group coming off of some side. So I'm just going to call this EWG. And like we said, this group, if it's a good leaving group, leads to higher reactivity. All right, so let's really briefly review this. So we'll go ahead and do functional group. I'll label its electron withdrawing group here. And then we'll look at the, actually, let me change this. pKa of conjugate acid for leaving group. All right, so the first main one we looked at yesterday, we learned how to name. These were acid halides or acyl halides. We change out that oic acid to a YL, right? So acetyl chloride, for example, was an example we looked at. If we think about the leaving group here, it would be Cl minus popping off as our leaving group. All right, if we think about the pKa of the conjugate acid, all that means is what's the acid if that leaving group were to pick up a proton? That would be HCl. We know HCl is a really good acid that has a pKa of about -8. So we can tell it's a really good leaving group because it's the conjugate base of a strong acid. All right, next, we'll look at this functional group. Actually, I'm just going to leave this as an acetate there. What's this functional group called? The entire thing, not just the part circled in green. Anhydride. So if we think about this one falling off, it's got a negative charge, which means its conjugate acid would be this acid. What's that called? Acetic acid. The pKa of acetic acid is 4.76, so you can see this is a lot less reactive than acid halides because every pKa unit is an order of magnitude. So this is significantly less reactive than acid halides. And then we can 4.76, you're correct. I misspoke, or miswrote, I should say. All right, next one, we've got esters. If we think about the leaving group in this situation, it would be an alkoxide. All right. The pKa of most alcohols is going to be right around the 15 range, so you can see the pKa is jumping up rapidly. These are way, way, way less reactive, which is good, right? We've got esters in our body. Fats are really just esters. We don't want our fats to randomly react. Well, maybe we do. Depends. And then last but not least, we've got our amides. We're going to kind of skip nitriles until the end. And the conjugate base for this is one of our super duper strong bases, right? We actually use this base to deprotonate alkynes and all sorts of things. So if we think about this, the conjugate acid is ammonia, which has a pKa of about 38. So really we can use this leaving group ability as a way of predicting how reactive our carboxylic acid derivative is going to be. All right, so now let's take a look at something we kind of covered in our pod. This is called nucleophilic acyl substitution. And I'm going to first do this under basic conditions. Like we saw last chapter, we have to be careful about charges depending on whether or not a reaction is run in basic or acidic conditions. All right, and under basic conditions, there's no acid, and normally your nucleophile has a negative charge, which is why the conditions are basic. All right, so what do you think the first step's going to be? attack. So the other way of thinking about the reactivity is the more electron withdrawing that group is, the more electron deficient that carbon is, the more electrophilic it is too. So it's kind of got a dual benefit here. All right, so this could be considered under equilibrium depending on your nucleophile. Because if your nucleophile is also a good leaving group, you can imagine a situation, you don't need to draw these arrows, but if your nucleophile is a good leaving group, meaning a better leaving group than your electron withdrawing group, you could kick it off and go right back to your starting material. So there are some situations where this is under equilibrium conditions. All right, what do you think happens in the next step though if we're going forward, not backwards? Yep, just kick off your electron withdrawing group. We just went over how they can be pretty good leaving groups. So this kind of reaffirms why there's higher reactivity, right? Not only are we kicking off something that's stable, but this carbon right here, if it's attached to a really strong electron withdrawing group, it's going to be even more electrophilic than normal. All right, so we can do the same thing under acidic conditions. You're probably getting tired of me going over this again and again and again, but I really, really want to drive this home. One common mistake I see students make is they show this as an SN2 reaction and they don't show this tetrahedral intermediate. It's really important that we show the tetrahedral intermediate. All right, so the next one is under acidic conditions. All right, under acidic conditions, you typically have some sort of catalytic acid floating around, and your nucleophile, because it's under acidic conditions, won't have a negative charge most of the time. It'll normally be a neutral nucleophile, usually with protons coming off of it. All right, what do you think the first step is? Protonation of the carbonyl, right? You could protonate your nucleophile, but that doesn't really take you in any sort of useful direction, so we don't need to show it. All right, now we've got our nucleophile kind of floating around, just like we saw in our problem of the day. This nucleophile can attack in because that positive charge is shared between that carbon and the oxygen. We had to protonate this though in this situation because if you have a weak nucleophile, but your electrophile is not strong enough, you just don't get enough reactivity for this reaction to occur. So now when our nucleophile attacks in, oops, we have our electron withdrawing group kind of floating around still. We've got a few options, right? What do you think an option is? Yeah, let's just deprotonate and show all of the steps. So I'll just write minus H plus. All right, what would occur next? Yeah, we could kick off our leaving group. It depends on the nature of this leaving group, right? If it's a really good leaving group, we'll do the following. If it's a really good leaving group, it's quite simple, right? We just kick that off in one go. And then we can deprotonate this to get to our final product. Right? However, in our pod, we saw that we had an ester. Esters, that oxygen isn't a good leaving group on its own, unlike a halogen, which is. So what might we need to do if we're running into a situation where we've got an ester? Yeah, protonate our electron withdrawing group. If that's the case, then what we need to do is to protonate our electron withdrawing group first, right? So I know this makes our notes a little confusing, but I did want to kind of emphasize it. Because right now, it's a good leaving group, or I should say better leaving group, just so we're clear. All right, and then same sort of idea as before. Now that it's a better leaving group, we can clamp this down, kick this off. And then we can deprotonate. So it does really depend on the situation, right? We really have to look at that electron withdrawing group and ask ourselves, is this a really good leaving group? Is it something that we would classically see in an SN2 reaction as a leaving group? Or is it not a good leaving group? We saw in SN2 substitution reactions that alcohols make crummy leaving groups unless we protonate them or tosylate them, right? So we can use those same trends to kind of predict what's occurring here. Does that make sense? All right, so now let's take a look at an example. I'm kind of cheating for some of you because you'll need to do this in your lab report. So some of you did this pathway. I can't remember which color it was, where you made meta-nitrobenzoic acid. And then for your very last step, you added in methanol and you added in sulfuric acid. Let's try to show the full mechanism for this complete transformation. So first step, what should we show? Protonation of the carbonyl oxygen, right? So all of this should look pretty familiar, where we're going to protonate that carbonyl oxygen. All right, now that we've done that, we've got methanol floating around. Methanol, in this case, is our only available nucleophile, right? We don't really have any other nucleophiles that can do anything. All right, so just like we saw before, this is a neutral nucleophile, so this is going to kick in. All right, so we're getting there. All right, like we saw before, we can deprotonate to get to our neutral intermediate. Oops, I forgot my NO2. All right, if we look at our final product though, we want to keep one of these oxygens, right? We also want to keep that OMe group on there, which means we need to assess whether or not this is going to be a very good leaving group. What do you think? It's a bad leaving group at this point. So it's a bad leaving group, which in this case indicates we need to protonate this first. So I'm going to go ahead and just write plus H plus. All right, by doing this, this is a better leaving group. So I'll even go ahead and indicate that, better leaving group. Because when we kick it off, it's going to be a neutral molecule. All right, so next step, we've got some decision making. We need to kick off that leaving group. Which oxygen's lone pair should I use, the alcohol or the OMe oxygen lone pair? Yeah, the alcohol lone pair. And kick this off. Yeah, that's a good question. So let's try to show this first, and then we'll come back to that. Is that okay? All right, so the question was, why didn't we use the lone pair on the oxygen with the methyl group? Well, let's think about that, right? Let's imagine, hypothetically, if this methyl group were swapped with that hydrogen, right, that I've highlighted. Yeah, it would be very, very hard to take off a methyl group and stabilize the molecule, right? Does that make sense? So let's just, for the sake of argument, don't copy this down. How would we get from here to our final product?
I see, but
yeah.
We didn't know the final product.
Yeah, if we didn't know the final product, we could propose this as an intermediate. It's just a really, really unstable intermediate. In fact, this would quickly react to kick electrons over there, right, through resonance, and then we would deprotonate the oxygen. So it just makes a lot more sense to use that oxygen there.
Oh, yes.
All right, so like we said, by having that hydrogen up here, we can just write minus H plus, whoops, and get to our final product. So it's a kind of cool reaction. In fact, this is called a Fischer esterification reaction. Esterification, like we're making an ester, right? So you might be familiar with Fischer, right? For better or worse. He's done a lot of important contributions to organic chemistry. But this was pretty cutting edge at the time. Basically, it said you can have a carboxylic acid, and if you have acid and an alcohol, you can make an ester. Pretty cool reaction. Like I said, we showed you previously how to make esters the other day using alkyl halides. What was the problem with that one? Or we said, well, why don't we just deprotonate this carboxylic acid and have it react then as a salt with methyl bromide? What was the problem? Do you remember? Causes cancer, right? In this one, we used methanol and sulfuric acid. None of those cause cancer, right? So this is a lot better. In addition, what do you notice about the acid? It's catalytic, right? So we don't need very much acid to drive this reaction to completion. All right, flip side of this. This is under equilibrium control, right? So theoretically, we could convert from our final product, the ester, all the way back to the carboxylic acid. How can we try to push this towards the ester side and avoid it going backwards as much as possible? Meaning, how do we favor as much product as possible? Remove water, right? So we could remove water as a byproduct from this reaction. So if we absorb the water from the reaction or distill it away, that's a really good approach. What's another approach we could do? So acid's catalytic, it really won't change much, but you're on the right track. We could increase the methanol concentration. So typically with these esterification reactions, we're trying to utilize Le Chatelier's principle to push this as much as possible towards the product side. Does that make sense? All right. So a lot of these reactions do look pretty big and crazy, and they are steppy, but they're the exact same trends we've kind of been seeing the whole term. All right, so that's kind of our intro. I really encourage doing as many mechanisms as possible just to drill this in. Sometimes students look at this on exams and their brains just freeze up because it looks complicated and it's steppy, and it is steppy, but I wouldn't necessarily say it's complicated. You just need to be comfortable with the individual steps. Yep.
Do you want us to show those intermediates like
removing the hydrogen and then adding the...
So for example, this whole step right here, where we removed a proton and added it, you can condense it and say plus minus H plus. I'm totally fine with that. Yeah. Yep. All right. So now let's jump into the fun stuff. We'll go into acid halides first because we know they're the most reactive. Arguably, they're the most useful building block that we'll see in this chapter. All right. So overall, let's say we have a carboxylic acid. Carboxylic acids in and of themselves aren't super duper reactive. They do simple acid-base chemistry. But what we can do is convert this to its more reactive cousin, the acid halide. All right, does anybody remember a simple route for removing or changing an alcohol to an alkyl halide? What was that? Sokol. Sokol 2. Thionyl chloride, right? So thionyl chloride will actually work for this as well. It's a slightly different mechanism, but it'll get you to that acid halide. The byproducts for this are similar to what we saw before. We get sulfur dioxide gas that will bubble out of solution and will also generate HCl as a byproduct. So let's take a look at the mechanism. I think this one works without pyridine. I would have to look that up though. All right, so this mechanism is a bit strange. But one thing I want you to remember is that thionyl chloride is like the king of electrophiles. It is really, really, really electrophilic. It desperately wants electrons from anywhere it can get it. All right, so what we can do is take electrons from this oxygen, kick them up to this oxygen. That's essentially just a resonance structure, right? So I'm pushing electron density onto that upper oxygen, and then that oxygen can attack into the sulfur and kick electrons up to that oxygen. All right, so now we've got this intermediate. It's pretty highly charged. The next step I've seen shown a few different ways. Some people show deprotonation. However, in our textbook, I believe they show kicking off of one of these chlorines as a leaving group. And I believe the reason they show it this way is because once you kick off chloride, chloride's not a great base, but it's a decent enough base to do the next deprotonation, or even better yet, it can act as a nucleophile. In this case, deprotonating that oxygen doesn't really help you because then that carbon becomes less electrophilic. So chloride in this case can attack straight in. All right, so we're making progress here, right? The next step is kind of complicated. It's weird to think about this, but this is a really, really good leaving group. And so is this. Both of those are great leaving groups because if you kick them off, we generate SO2 as a gas. Anytime you generate gas as a leaving group, makes it a super great leaving group. So in the next step, I'm going to clamp this down, kick this off, then kick that off all in one go. That leaves us with our carboxylic acid plus SO2, which we said is a gas that'll bubble out of solution. This oxygen still has a proton on it, excuse me. Oops, And this should be a chlorine. Holy cow. And then we have Cl minus floating around. So at this point, your chloride can act as a base. Like I said before, in this reaction, it acts as both a nucleophile and a base. All right, so now we've made our acid halide. Does that make sense? I think you sometimes see this run in pyridine. The interesting thing is pyridine we think of as a non-nucleophilic good base solvent. But in reactions with acid halides, it'll actually react with the acid halides and give you this really unstable intermediate. But sometimes that's a good thing. However, I think in our textbook they avoid showing pyridine in there. Does that make sense? All right, so now let's look at hydrolysis. So hydrolysis, if you break it down to its elements, it means water breaking, right? So water is going to break this apart, and what do you think we're going to make? Carboxylic acid, right? So in this case, the question is, what do you think will occur first? We don't have any acid around. This one's kind of the odd one. Acid halides are so reactive, you don't even need to protonate the carbonyl to get the water to attack in. They're just so insanely reactive, water's good enough. So in this case, you don't need any sort of acid catalyst. And then in the next step, you've got a few different options. Doesn't really matter to me which order you show them. You can either kick off your leaving group or deprotonate. I'm fine either way. We'll just kick off our leaving group first. And then last but not least, we can deprotonate to give us our final carboxylic acid. And then if we just want to run around in a circle all day long, we can re-react this with SOCl2, our thionyl chloride, to regenerate our acid halide. Like I said, I think I mentioned it the other day, these are often found in tear gases, right? So if this is in tear gas, we've got moisture in our lungs and in our eyes as water. Water will react with those acid halides. And if you think about the byproduct for this reaction, we kicked off HCl. So you're basically generating a small amount of HCl on the membranes along your eyes and in your lungs. Yeah, so your body desperately is trying to flush this acid out of your mucous membranes, and that's why your eyes start welling up. You start coughing, trying to get it out of your lungs. It takes a really small amount of this stuff to be quite uncomfortable with. All right. All right, next one's pretty similar. We won't do the full mechanism because it's so similar. But this one generally requires a small amount of base. So oftentimes you see pyridine used as a base. And in this one, you can imagine we're going to swap off that chlorine and make what new functional group? An ester, right? So the alcohol is going to add in here. So you can use this to make esters from carboxylic acids. Like I showed you previously, though, most people use the Fischer esterification. But why might you use this one over a Fischer esterification? Well, that, and we're not using any acid in this step, right? So theoretically, you could use this as a workaround. However, normally to make your acid halide, you're producing acid as a byproduct. So this isn't a super popular route. All right. All right, next one, same idea. This one's kind of nice. This could be really any primary or secondary amine. Doesn't really matter. Both of those can act as nucleophiles. However, in either case, you can use excess. And why might you use excess rather than one equivalent? Pushing the reaction, that, and if you remember up here, we added pyridine as a base. In this case, your amine could act as its own base too, right? So it's doing double duty as a nucleophile and its own base, which is kind of handy. So let's go ahead and consider, our options for the top reaction. We could make that, right? Or we could make that. You could also do this with ammonia as well. However, typically it's a little harder to handle ammonia, but you get the idea. I will say there's much, much better techniques available for making amides. So note, this is old school. There are better options. All right, and then let's see. We'll do one last one and call it a day. Reduction. So let's say we want to just go ahead and convert this to an alcohol, right? Primary alcohol. What do you think we might use? LAH, why not? You typically use this in excess followed by H2O. And you can imagine that this mechanism is pretty straightforward, right? We've essentially got H minus floating around that can kick up. Oh my goodness, why is that doing that? Then in your next step, this will clamp down. It's really hard to stop at the aldehyde at this point. So you would use your second equivalent of your lithium aluminum hydride, which in this case I'm just going to show as H minus. Kick electrons over. And then last but not least, we can protonate in step 2 with our weak acid. So really similar reactivity to what we saw with esters, right? But in this case, even way more reactive than esters. So this will just keep on going. Make sense? All right, so that's where we're going to stop today. Tomorrow, I'll show you some newer reagents that we haven't seen before, but I think that's enough for today.